Hey everyone, it's Justin again. In this lesson, we're going to be looking at the form of exponential functions. We'll learn about the different variables that make up the equation of an exponential function, what they each mean, and what they can help us determine about the graph of the function. Before we start learning together, you have a discovery to complete on your own. In your PDF, you'll find the GeoGebra activity titled Exponential Functions Exploration. If you haven't yet completed it, pause this video here and go complete the activity now. I'll be waiting for you when you're ready to come back. On GeoGebra, you were working with equations that looked like this, but we had sliders for the variables. Exponential functions take the form y equals a times b to the x power. Let's look at the variable a first. In the exploration, this was called the leading factor, but now we know that its proper name is a. What did you find out? I noticed that when you change a, it doesn't change the shape of the graph, so what is it doing? When we make a 3, our function changes a little around the y-axis. The function crosses the y-axis at 3. So the y-intercept is the same as the a value? Well, that can't be a coincidence. Let's change a to a fraction, like 1/4, and see what happens. Wow, it makes our y-intercept 1/4. So a is always going to be the y-intercept. That means in the graph of an exponential function, we know that the y-intercept is 0, a. Now what about b? You saw the effect of b in part 2 of our exploration. It was called the base of x, but now we know that its proper name is b. What did you find out? In this graph, the b value is 2, but what if we change it to 8? Whoa, our graph's y values become large very quickly. So changing the b value affects how steep our curve is. B, the base of the exponent in an exponential function, is called the growth rate because it tells us how quickly the outputs grow, which we can call the steepness. I wonder what will happen if we make the b value very small, like a fraction. Let's change our b value from 8 to 1/8. Wait a minute. This graph seems like it's the same steepness, but now it's backward. The growth rate of our function affects the graph in another way. The b value impacts whether the graph is increasing or decreasing. When b is less than 1, but greater than 0, like a proper fraction or a decimal, the graph is decreasing. We call this exponential decay since the y value is decaying or shrinking as the x value increases. When b is greater than 1, we saw the opposite. The graph was increasing like we saw here with b equals 8. We call this exponential growth since the y value is growing as the x value increases. Let's check our understanding by working with different a and b values. Okay, we need to match these graphs to their respective equations. What do we need to determine in order to do that? Based on our a and b values, we can tell a few things. Remember, our a value is our y-intercept, and our b value tells us our growth rate, which signifies steepness and exponential growth versus decay. Pause the video and try this question on your own. Let's work through this together. I notice that our first graph looks like it's increasing, meaning that it's an example of exponential growth. What does that tell me about the equation of this curve? If it's exponential growth, then b has to be greater than 1. For our second graph, it looks like it's decreasing, meaning that it's an example of exponential decay. What does that mean for the b value of this equation? Since this curve represents exponential decay, the b value has to be less than 1. Well, I know that the first graph has to have a b value greater than 1, so it can't be a or c. It has to be b or d. And likewise for the second graph, if b is less than 1, then it has to be a or c. So how do we narrow down our choices further? Let's figure out what our y-intercept, or a values, are for each function. We can see that the first graph crosses the y-axis at the point 0, 3. So our function must have an a value of 3. So it can't be b, and this graph must go with d. What's the y-intercept of the second graph? It's 1, so it must match with c, not a. It's important to recognize that we could have come up with our answer a couple of different ways, but it's good to be thorough. Let's look at another example. Our second problem asks us to identify the key characteristics of each function and decide which graph will be steeper. It looks like we're looking for the y-intercept, the growth rate, and whether our function models exponential growth or exponential decay. To test our knowledge of growth rate, we can also determine which graph will be steeper. Keep in mind the form of an exponential equation, and pause the video to try these questions on your own. How'd it go? For our first equation, to find our y-intercept, or a value, we just look at the value in our equation that is not raised to an exponent. And that value is 3/4. Wait a second. The a value is 3/4? That seems weird. Is it even possible for a function to have a y-intercept at 0, 3/4? Well, sure. The functions have fractional coordinates all the time, so my y-intercept must be 0, 3/4. Whew, I'm glad I looked at my equation carefully. Now, what's our growth rate? We look at the number that's raised to the power of x, and here it's 3. Then we decide whether our function models exponential growth or decay. How can we tell whether a function models growth or decay? Our b value tells us that. If it's less than 1, it's decay, and if it's greater than 1, it's growth. So what do we have here? Well, since our b value is greater than 1, it models exponential growth. Let's check our work on the next one. Our a value is 5, so our y-intercept is 0, 5. Our growth rate is the improper fraction 19/3. So does this model growth or decay? We've said that our function models growth when we have a b value less than 1 but greater than 0. Is our b value greater than 1 or less than 1? Don't let the fact that it's a fraction fool you. 19/3 simplifies to 6 1/3. So it's greater than 1, meaning it also models exponential growth. Ooh, those fractions were sneaky. I guess we've learned that it's important not to just look at the numbers in the equation, but to take the time to think about their value and what they represent. We have to remember that growth versus decay is determined by the b value being greater than 1 or less than 1, but greater than 0. Lastly, we need to figure out which graph is steeper. How do you think we could tell which graph is steeper? Well, since they both represent growth, it's a matter of which one is growing faster. Which b value will increase more quickly? It's going to be the larger number. In this case, 19/3 is over twice as large as 3, and that means the graph for y equals 5 times 19 divided by 3 to the x power is steeper. Awesome. Let's talk about what we learned. This knowledge of the form of exponential functions will become really useful once we start graphing. We'll be able to look at the a value and graph a point immediately, the y-intercept. Then our growth rate will tell us what we should expect in terms of steepness and whether we'll have exponential growth or exponential decay. That concludes our guided notes. You'll finish up this lesson with your online practice. Good luck with that, and I'll see you next time.